This conference will now be recorded.
Alrighty, so today, a couple things to go over before we get into today's lesson. I've been asked to remind everyone, if you haven't yet set up a payment plan or had financial aid, if you were applying for that come through, you need to make sure you set up some sort of a payment plan for classes. Otherwise, over the weekend, you're going to be dropped from your courses. And when you get dropped from your courses, then you're going to have to hunt down people for signatures, and you're also still going to have to create a payment plan. So you want to make sure you do that before you get logged off of there. All right. I do have some people who are not logged in and trying the homework assignments yet. Remember, we have some of these things due tomorrow. So, and it's nothing that you can get done within an hour's time. So you want to make sure that as soon as we get off here, if you've got some spare time, you want to start getting through and start working through some of those problems there. We also have online quizzes and videos available and such. So speaking of the videos, I want to point out that if you missed last week's session, I'm trying to get the YouTube channel back up and going. I usually had a YouTube channel that I can throw things into. So as soon as I get that going again, I'll put the link to that. But in the meantime, I will be posting our weekly synchronous sessions. So if you did miss our session last week, you can see it. I'll be posting those here. So remember, I go through things in a very abbreviated version because I only have an hour with you. So I'm trying to hit the most important parts of this. If you do need additional help, remember you can click on assignments and the assignments are going to show up. And let's say you want to start working on section 2 homework. So if I click on that, it's going to take me to the homework problems. Remember, you got to scroll down to all of the homework problems. Okay, so section 2 is 18 problems and some have multiple parts. And so if you keep scrolling down, here's where you can start to see the videos. So you can pull up the videos in just parts. So if you're still having a difficult time with, one of the questions up above, you can scroll down a little bit and you can pull up the videos. And remember, these are through my friend Becky. So she has prepared these for us, and she actually goes through all the problems in the book. So remember, your book is considered a workbook, and you want to treat it as such. So it's there to write in. So that's what I want you to be doing. Write those answers in, get that that memory going when you're looking at things, when you're writing it. Just by simply looking it over is not going to be enough of a connection for you to make sure you're doing well. You don't want to get behind in the homework because as soon as you get behind, I've got cutoff dates. So the homework will shut off at the due date and time. And remember, those of us in the central time zone, these things default to Indianapolis time zone. So if it says 11:59, remember that means 10:59 our time. So you always have to do that a little bit earlier there. Okay. Alrighty, so let me see if I've got any other housekeeping items here. Okay. So I just wanted to make sure that everyone knew where to find all of this information. So today we're going to continue on. We're still in Module 1. We're going to go on to section number 3. And section number 3 has scientific notation. Oh, I always want to click on the wrong icon there. So here we have scientific notation. And so we're starting here on page 23 in your book. And you can see in order to understand scientific notation, we first have to understand powers of 10. Okay, because scientific notation is based on powers of 10. And also, notice that anytime we start to change the name of the unit here, that's usually after every 3 numbers here. So after we jump, we say 3, and then we go to the next unit. So in this case, we start out with the number 1. So this is what the number would look like in standard form. Powers of 10, well, there are no powers of 10, so that means the same thing as 10 to the 0 power. 10, that's 1. There's 1 power of 10 there, so that's 10 to the first power. 100 is the same thing as 10 times 10, so that's 10 to the second. 1,000 is 10 times 10 times 10, and 10 to the third, and so on. Now, the ones that we are going to be using the most often in our class are going to be thousands, and so know that that's 10 to the third. Millions, which is 10 to the sixth. Billions, which is 10 to the ninth. And then trillions, which is 10 to the 12th power. Okay, so definitely want to get to know those, because that's what we're going to be using as we go out. Now, there's multiple ways to say some numbers. There we go. When we see a number such as this right here, how would I say that? It's okay to say it both ways. We can say 1,200, or we can say 1,200. Both of them are acceptable to say it, because I've got 12 of these hundreds, or I've got 1,000 and then 200 here. So sometimes we need to abbreviate numbers to make them easier to work with. And I'm going to kind of go back and forth between very large numbers and very small numbers. So when we're dealing with numbers that are very large or very small, we've got to put them in our calculators and do calculations with them. Well, sometimes there's too many digits to put in there to be able to get the appropriate calculation. So we have to do the next best thing, and that is to abbreviate the numbers based on scientific notation. Now remember, scientific notation is based on powers of 10. So these are our place values here. So, we consider the decimal point at the end of a very large number right at the end, right on the right-hand side. So think of, a very large number, think of money. Money, the decimal point's always at the end on the right. And so you see we have our ones, tens, thousands, millions, billions, trillions, okay, that we deal with here. So how would I put a very large number into scientific notation form? So let's take a look at what the definition says here. Okay, so the procedure for writing says step number 1, move the decimal so there is one non-zero number in front of the decimal point. Okay, what in the world does that mean? Okay, look at this number 12,000. I want to abbreviate this and make it a little bit more user-friendly to use a calculation with this. So what I'm going to do is I'm going to replace the decimal. So notice this arrow right here is where we're replacing the decimal. And it is going to go between the 1 and the 2. So now there is one non-zero number in front of the decimal. So in other words, it's not a 0. It's the counting numbers 1 through 9. Another way of thinking about this is I've replaced the decimal, so now I have a new number between 1 and 10. And the number 1.2, yes, that makes sense. It's between 1 and 10. And notice I didn't worry about these extra zeros here. Okay, we're going to talk about those in just a moment. Now, the second part that I want to put the number in scientific notation is to write this number times the corresponding power of 10. Well, how in the world do I know how many powers of 10 I need here? So what we do is think, if I put the decimal between the 1 and 2 to turn it into scientific notation, how many places do I need to move it to get back to the original number? So in this case, I would need to move it over, what, 1, 2, 3, 4 places to the right. And if we remember, a number line going to the right is the positive direction. So in this case, this would be 10 to the positive 4th value. Okay, so this number would be what it would look like in scientific notation form. So now if I look at both of these numbers here, the first number, okay, which is the approximate population of the United States. We can abbreviate this in scientific notation form by step number 1, replace the decimal. So you have one non-zero number, or you got a number between 1 and 10. So I'm putting it between the 3 and the 2. Okay, I'm not worrying about these extra zeros here. Okay, now I'm going to multiply it by the power of 10. How many spaces do I need to move to get back to the original number? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, notice that the powers of 10 are not the number of zeros. For some reason, a lot of students think it's the number of zeros that are present. Okay, there might not be zeros present on a number, so be careful with that. Now, we like to abbreviate numbers in this, especially in the news. So something like this, 7.3 billion. Well, this is easy to turn into scientific notation. We can just take it, and we know billions from, remember our previous page, is 10 to the 9th power. So we can just say 7.3 times 10 to the 9th power, and then I'm all done. I'm in scientific notation form. Now, what does this number mean, 7.3 billion? This means the same thing as having a comma there when we write the words. In other words, 7,300,000,000. Okay, that's what that number would mean. We just, for some reason, we just like to abbreviate numbers that way. Now that's how I turn a number that is very large into scientific notation. We can also do the opposite end, and I'm going to jump ahead just a little bit to get to that section right here. Okay, and we can take numbers that are very, very small. So if I'm thinking of numbers that are very small, we can think of these place values. Okay, so now I'm going, and the decimal point is on the left-hand side, and I'm working to be a smaller number. So 1/10, okay, would be 1 over 10, or 10 to the negative first power, okay? 1/100th would be 10 to the negative 2 power, okay? Because if I am converting now between standard form and scientific notation, remember I would have to move 2 places back to get to my original spot. So when numbers are very, very small, we're dealing with negative exponents. So let's take a look at this example here. Same rules are going to apply to put it into scientific notation. It's just that the decimal point here is now on the left-hand side. So step number 1, I need to replace it. So I've got a non-zero digit in front of the decimal, or I've got a new number between 1 and 10. So if I'm putting it between the 2 and the 4, I've got 2.45. Now once again, I'm not worrying about these zeros because these are just holding a place here. They're just holding a place so that I know where the actual number begins. Okay, then I'm going to multiply by a corresponding power of 10. Well, if the decimal point has been moved here, that means I'm going to have to go 1, 2, 3 places to the left. And remember, on a number line, to the left is in the negative direction. So that means my exponent is going to be to the negative 3rd power. Okay. So here's how we would convert these two numbers into scientific notation. Remember, step number 1, replace the decimal. So now you got a number between 1 and 10. Step number 2, multiply by a power of 10. And that's how many places to get back to the original number. Remember, it doesn't mean how many zeros, how many places I have to move. Okay. So I want to jump back again, because I kind of like to cover both of these at the same time, because it makes sense to do the very small and the very large all at the same time. Now, here's some other numbers in scientific notation form. Sometimes I like to start with the number here and millions being In this case, let me see if it'll let me add that. So what I like to do is start and say 92.96 times 10 to the, well, I know millions is to the 6th power. Now, I know this number is not in scientific notation. Okay, hint, hint, this might be a quiz or test question, making sure a number is correct. Okay, just because it has a power of 10 doesn't necessarily mean it's the correct version of the scientific notation. So to go from this abbreviated version, because I know millions means 10 to the 6, to go to actual scientific notation form, I would need to move that decimal place back one extra space. Now let's think, if I'm here, that means I'm going to move 6 places to get back to the original number. But if I have to take a step back, not only do I have to take that step forward, but then go 6 more places. So in other words, the final version would be 2.96 times 10 to the 10th power. Okay? Same thing over here. So if I wanted to rewrite this one, I can start with 0.86 times 10 to the, well, I know millions means to the 6th power. Okay, so if I'm here, and to get to the original number, I'd have to go 6 places to the right. But to turn it into scientific notation, I had to replace the decimal in between these 2 digits. So that means I already took a step in the correct direction. So that means in this case, it's only 10 to the 5th power when I've got it in the appropriate scientific notation format. Okay, so be careful when you're going back and forth between those 2 versions. All right, now when we're going to start to do calculations involving numbers with scientific notations, we have to keep in mind what we refer to as significant figures. So what I want you to do is in your book, I want you to take out page 231 and 233, and you're going to replace them here in section 3. Okay, so do that now. If you've got your book in front of you, take page 231 and take page 233 towards the back, replace it, put them back over here so that you can refer to them easier here. I've already started to have questions about this in the past week, and some people are not getting the answers correct on WebWorks, and that's because they don't have the correct number of significant figures. So we're going to talk about that and how that applies. How do I know that they're significant? How do I know how to do operations with that? So let's look through the rules here. First of all, any non-zero digit is considered significant. So the counting numbers 1 through 9, okay, any of those would be significant. So in this case, the number 47, both of these are significant, so I have 2 significant figures. 3.14159, you should recognize that as the first few values of pi. Every single one of them is a counting number from 1 to 9, and so there are 6 significant figures there. Okay, now the next one says zeros appearing anywhere between 2 non-zero digits are significant. So like the number 401, okay, the 0 is in between these other numbers, so all of them count. So I have 3 significant figures. In this case, 3104.05, the zeros are between the other digits, so all 6 count. Okay, so 6 significant figures. Now, in decimal numbers, okay, this refers to numbers that are in decimal format. Leading zeros, in other words, zeros to the left, are not significant. So I already said that before. So this number right here, 0.000314. These 3 zeros are just here simply to hold a place value so that the digits start in the correct place value. So those are not significant. So in this case, I only have 3 significant figures. Okay. Okay. Now, in decimal numbers, Trailing zeros, in other words, zeros to the right, are significant. They are significant. So when I have a decimal number such as this, 3.140, it is significant in a decimal number such as this because they actually went to the point to show that zero, that there was nothing after that. It ended in that 0 digit. So because they actually added that, all 4 of those would be significant figures. Now it says in numbers without decimals, zeros may or may not be significant. How do I know? Well, let's take a look. In this case, 35,000, it shows that we have at least 2 significant figures here, the 3 and the 5. And in this case, the zeros are just place value holders. But in this case here, with this number, it's not a decimal number, it's a whole number. But notice underneath that last digit, it's underlined under that 0. So in this case, because it's underlined, and you might also see it in some cases where there's a bar above a digit, whenever you see like an underline like that or a bar above, that means we want you to carry it out to that digit. So it's significant enough for us to put a little extra figure there. So yes, this one would have 4 significant figures because we're telling you so. We're telling you go out to that 4th significant figure. All right, so you're going to have to remember this when you're going to be doing the assignments here. Now, how do I multiply and divide with numbers that have significant figures? Let's take a look. So in this case, I've got a 3-digit number, 3.45, times a 4-digit number, okay, 12.56. So look at the rules here. It says when we are multiplying or dividing numbers, we should round the result to match the same number of significant figures in the least significant number. Okay, the least significant number. So this one has 3 digits. This one has 4 digits. So that means after I multiply those two, and here's what I get after I multiply, I have to round to the least number of significant figures, which is 3 digits. Okay, so notice the 3 digits would end at that first 7, but I have to round appropriately. Since the next number after I cut it off is a number greater than 5, that's how this 7 turns into this 8 right here. You have to make sure that you are rounding correctly, otherwise it's going to mark it wrong. And when it comes time for a test or a quiz, I will also mark it wrong. Okay, so be careful that you're rounding correctly. Now dividing, same idea holds true when I'm dividing. Here's a 5-digit number, a 4-digit number. When I divide out, I've got this big old decimal value. And so I know the least number of significant figures is only 4. So I'm going to cut my answer off after 4 significant figures. Now this one does not have a number that's 5 or greater. So I'm going to leave the answer ending in 5. So 1.225. Okay. Now, also working with these significant figures, when I am multiplying or dividing numbers that are in scientific notation, what do? So in this case, here's what I have. I have 2 numbers in scientific notation. Let's see if it's going to let me put that in. Darn, it's not. Okay, I don't like the way they write this in our book here. I like to put a parenthesis in front of the 3 and a parenthesis here after 10 to the 3rd, because this represents the first number here, 3.75 times 10 to the 3rd. Then we're multiplying it times 1.2 times 10 to the 2nd. So you can put a parenthesis in front of the 1 and then after 10 to the 2nd. Okay, so it's one scientific notation number times another. Well, what I have to do here is 2 things. First, I have to take the decimal portions and multiply those. Okay, so if I multiply these 2 out, I'm going to get 4.5. No other digits. Then what I have to do is multiply the powers of 10. Now, if you remember, when I am multiplying powers of 10, these two numbers are in exponential form. 10 is the base number, and then I have the exponent that it's raised to. Now, according to the rules, whenever I am multiplying and I have the same exact base number, and in this case it's 10, what I'm going to do is add the exponents. So 3 plus 2 gives me 5. So this problem, the final answer would be 4.5 times 10 to the 5th power. Now, dividing numbers that are in scientific notation form, kind of similar. We're just doing a division operation. So here's the first number in scientific notation form, divided by the other. These are a little more easy to see. Once again, I'm going to worry about the decimal portion first. So when I divide that, notice I get the number 2, but the answer is 2.0. Now up here, I only had 2 digits in my final answer, but what if I had more digits when I multiplied? I have to follow the rules for significant figures in both of these cases. So in this case, it was kind of beneficial because it only had the 2 digits, but notice I had a 1.2 and a 3.75, so I had a 3-digit times a 2-digit. That means my answer could only have 2 digits in it. Okay, and it just so happenly worked out in that case. In this case, when I divide the decimal portions, I get the whole number 2, but there's 2 significant figures here in both cases. So the least amount of significant figures is 2, and that's why we actually put 2.0 in. Okay, that's why we did that. Then in this case, we're going to divide with the powers of 10. Now, dividing with powers of 10, in this case, we are going to be, when we're dividing, we're going to be subtracting the exponents. So that's the quotient rule that they say. So as long as the base number is the same, we're going to take the numerator minus the denominator. Okay, so those exponents, numerator minus denominator. And you want to be careful because it does make a difference what order you do it in. Because in this case, they're both positive, but what if one were positive and one were negative? If you've got that case, you want to make sure you're plugging it into your calculator correctly. Let's pretend that the denominator was a -6. In my calculator, I'd have to say 9 minus a -6. Okay, and that would give you a different answer than 3, because 9 minus 6 is 3. So be careful if those exponents are positive or negative, because it does make a difference. And you always have to take numerator minus the denominator. Okay, so be careful when you're going to be working and doing your problems, putting things into scientific notation or actually performing some operations and working things out, because you need to make sure you have the correct significant figures. Okay, so let's go back now to our section. Okay, I think we already did that. Alrighty, so let's take a look at these two. Okay, so I would multiply the decimal portion. Okay, notice my answer can only have 2 significant figures in it. So I'm going to have to round appropriately. Okay, and then I'm going to multiply the powers of 10. So if they're the same base, I add the exponent. That's how I get the correct number. Now, look at this. It says, wait, if I add 9 and 5, I don't get 15. But this is because in this case, when I were to do this, if you were to do this in your calculator, in this case, you're going to get not just a regular number, but you're going to have something that has multiple decimals in it. Let me see if I've got this one written in my notes because I like to have those. Okay, so when you do that, well, let me put it into my calculator and tell you all the rest of the digits here. If you take 5.92 times 6.3, you're actually going to get 37.296. Okay, so let me put this in here so you can see how we put it back in. 37.296, and then we know the powers of 10 times 10 to the 14th power, because 9 plus 5 is 14. But remember, in this case, this number is not scientific notation form. I have to further adjust it. So if I'm here, I would move 14 places to get to the original number. But in order to turn it into scientific notation, I had to take an extra step backwards. So not only do I have to move forward one spot, but then my 14. So that's why the final answer is 3.7 times 10 to the 15th power. Okay. All right, number 8, I've got 1.9 divided by 4.62. In this case, once again, I'm going to have multiple digits here. So if I do this in my calculator, I'm going to have 0.41125555411. Whoa, that's a big number. Okay, times 10 to the what power? Well, 10 to the 13th divided by 10 to the 4th. Okay, so I have numerator minus denominator. So I have 13 minus 4. That's going to give me 9. Okay, but look at my answer. My final answer is a little different. So 2 significant figures, 3 significant figures. So that means I can only round it out to 2 significant figures. So I'm going to cut it off at this first one. Now, I also need to put it into official scientific notation form, which is a number between 1 and 10. So if it's like this to begin with, times 10 to the 9th, if I already move it one place in the direction I need it to go, all right, that means I only have 8 more. So that's why the exponent is 10 to the 8th power. All right, so be careful because you want to make sure you're doing this correctly, because if you're not doing the correct number of significant figures, or you're not converting it to scientific notation properly, it's going to mark it wrong. And hint, hint, these are good ways to try to trick people. Okay, so be careful with that. These are good ways to try to trick you. Now, it just so happens that if you have a scientific notation calculator, a scientific calculator, it actually has a function to put these into scientific notation form. Okay, and that's the double E button. All right, now in order to be able to use the double E button, this first calculator is the one that I have. I actually have to hit the second function and then this, because the double E is actually on the back part of the calculator. It's not actually on the front part of the button. So that's the second function of that button. That's basically what it's saying. So if I wanted to, do this problem right before it, I could put 5.92. Then I'm going to hit second and double E, or if you have a calculator that has the double E button, just hit double E. All right, now look at what double E means. Double E means it's automatically saying multiplied by 10 to the what power. It's asking you what power is it? And so I'm just going to put 5.92E and then the number 9. Okay, then times, then I'm going to put 6.3 double E, and then put the number 5 and then hit enter. So what this did is it automatically put the numbers into scientific notation form, and it's automatically going to give me the answer in the correct scientific notation. So just be careful. Sometimes you got to watch the digits once again. It might not be rounding it to the correct number of significant figures there. But that option is available to you on these calculators. Now, just a reminder, you are only allowed to use a scientific calculator. You may not use, I'm sorry, yes, a scientific calculator. You may not use a graphing calculator for the exam. So those $100 calculators, you're not allowed to use those on the exam, and they will be checking for those. So get yourself one of these. It only cost me like, I don't know, $7, $8 at Target. So that's what I got. And they sell them at the Ivy Tech bookstores, these types of calculators. Alrighty, so let's talk about some application problems using that. Okay, so here we go. Suppose that a state has a $31 million budget for the K through 12 schools. If that money is dispersed among 292 school districts, how much money will each of them get? So they're going to disperse it evenly. That's what they're saying, amongst the 292 school districts in the state. So in this case, I've got a number in the billions. All right, so I'm going to convert this to scientific notation. Now I can either say 31 times 10 to the 9th to represent billions, or I can further put it into the correct form. If it's here, I would go 9 places forward, but I have to take a step back to put it into correct scientific notation form. So that means my exponent changed to 10. Okay, so either of those would be okay to start doing the problem, because really what we're looking for, unless it says specifically to put all the numbers that you're multiplying or dividing into scientific notation form, you can worry about that at the end. Okay, and then the other number, 292, would be 2.92 times 10 to the second. So in this case, if I'm dispersing it, I'm basically dividing it up, right? So I'm dividing, here's the money, divided amongst those schools. Okay, and they don't have the same units. Remember, the one is in the billions, the other one's only in the hundreds. And so I get a decimal value. All right, and I have to convert this to the correct answer. Well, in this case, notice 3.1 or 31 only has 2 digits, and then 292 has 3 digits. So the least number of digits would be 2. So I'm going to have to round my answer to 2 significant figures. So it's going to be approximately 1.1, because if I cut it off right here, that 6 is going to increase that 0 to the 1. And then multiply it by the corresponding power of 10. In this case, it is 10 to the 8th power. Now, think about the correct form of the answer. If they're asking how much money will each school district receive, think about it. Would it make sense to say about 1.1 times 10 to the 8th dollars? I think if a news announcer said that, we probably wouldn't understand what they were talking about. So in this case, it makes sense to put the answer in standard form. So in this case, it's about $110 million, and that would be per school district. Okay, so they took this and they put it into standard format. Now remember, since we rounded it out to significant figures, we say approximately, and the way we say approximately is with these little squiggly equal signs here. That means approximately, because we were rounding. All right, let's look at another one here. According to the 2013 report from the Bureau of Justice Statistics, approximately 2.2 million Americans are incarcerated in local jails and state and federal prisons. If it costs $25,000 to house each inmate for a year, approximately how much is the US spending on incarcerations? Well, in this case, we have to think of the operation I'm doing is going to be multiplying, because I'm going to multiply the cost times how many people are incarcerated, right? All right, so in this case, it says approximately 2.2 million. So 2.2 million is 10 to the 6th power. So I'm going to take that scientific notation, multiply it by 25,000. In scientific notation is 2.5 times 10 to the fourth. Okay, I'm going to follow my rules here, and I'm going to round appropriately to 2 digits. And then I also need to make sure my powers of 10 are correct. So 5.5 times 10 to the 10th power is going to be the same thing as $55 billion. Okay, that's a lot of money on incarcerations. Okay. Here's another one. It's getting close to cold and flu season. Now think about this. I had a lot of people in my other classes that were getting confused what operation to use. It says it's estimated that a single droplet from a sneeze can contain as many as 200 million germs. If a sneeze is composed of 40,000 of these droplets, how many germs are in a single sneeze? Now think about it. It's saying one drop has 200 million germs. So I have one drop. But a sneeze has a whole bunch of drops. It has 40,000 drops. I'm trying to find the total germs. So in this case, I need to multiply. Okay, once I do that, I actually get 8 trillion germs. Okay, so that's kind of gross. And it's kind of funny because one of my very first teaching positions that I started with as I was taking my classes, I taught preschoolers, and the very first day we practiced sneezing properly. So we would sneeze into our elbow so that we wouldn't sneeze on our friends. So that was kind of funny. All right, so now that we know how to convert a number into scientific notation, let's look at some other ways that we can work with this. We're going to look at something called per capita. Okay, so I've skipped now to page 26. Okay, per capita means per person. So now I can take numbers and figure out a per capita. And sometimes they also refer to this as maybe like a rate, a kind of a rate. Now, here's just an example with something fun, the number of Skittles candy. Okay, if 200 million of these Skittles candies are produced in a day, and the US population is approximately 324 million, what's the ratio of Skittles to people? So remember, it's telling you how to write the ratio. Here's the first item, numerator. The second item is people. And we also know that if we're saying Skittles per capita means per person, so I'm going to divide by the number of people. So in this case, I notice that both of the units are exactly the same. They're both in the millions. That makes my life so much easier because I don't have to worry about putting these numbers into scientific notation. Since they're both the same units, they're going to cancel each other out. So if you remember the ratio, units cancel each other out. So all I have to do is worry about the numbers. And in this case, I get approximately 0.62 Skittles per person. Okay, so just under 1 Skittle per person per day. Now the next one, I skipped ahead. Let's look at the one with M&Ms. If there are 400 million M&Ms produced each day, can we find the number of M&Ms produced daily per capita using the same population as above? Okay, so per capita means per person. Once again, both of those units are in the millions. Makes my life easy because they're going to cancel each other out. Just have to do a division. And so that would be a little over 1 M&M per person. So that's if we were to evenly distribute that. Now, why do we need to know per capita values? Well, per capita values help us understand different kinds of things. Okay, so let me see. Let's take a look. We already went through the part on the scientific notation with smaller numbers, so I'm actually jumping to page 28 in your text. Okay, so if we know that per capita means per person, let's take a look and interpret a problem such as this. Whoop. So in this case, it says we're going to be trying to figure out the which country has the most Starbucks locations. All right. Now, when we're looking at that, as I look at the chart, and I'm just sheerly looking at the number of locations, I mean, we can easily see that the United States has the most. Okay, but sometimes we have to also put the number of the population in there because sometimes it makes a difference based on the population, which means how many per capita. Okay, so when I'm looking now and I'm going to be comparing that, but with the values with the population, I'm going to get something that's a little bit different. So notice, like here's Canada. We take the number of Starbucks locations and I want to find the number per person. How many stores per person is that? Well, that means I'm going to divide by the population. Well, this is a number in the thousands. This is a number in the millions. The units are different. So I'm going to have to use scientific notation here. Okay, I'm going to have to put the full version out there. And in this case, take 1.46 times 10 to the third power, divide it by, and I can, abbreviate this and say 35.2 times 10 to the sixth, because I'm really looking for at the end, what do I get? When I do that, I get this decimal value. Okay, notice it's a very small number. All right, well, if I take this number and I put it into scientific notation, I get 4.15 times 10 to the negative fifth. That's how many Starbucks stores per capita. Well, honestly, this number makes no sense to the general public. I mean, you wouldn't want to hear the announcer say that on the news. So what we like to do is to put it in a form of a value that's going to be a little bit more user-friendly and understandable. Okay, so what we're going to want to do is we're going to figure out the number of Starbucks per a group of the population. And in this case, they said, well, we're going to figure out how many per 100,000 people. All right, now, how do I do this? Once we get the per capita value, all we're going to do is multiply that decimal times the population we want to compare it out of. Okay, so in this case, we're going to take this times 100,000 and we're going to get 4.15. Okay, so if I were now the news announcer, I could say something, there are approximately 4 Starbucks per stores per 100,000 people in Canada. Okay, or 4.2 if I wanted to round it out to 1 decimal place. That makes a lot more sense saying numbers that way. Okay, so here are the values filled in. You definitely want to keep in mind when you see this, if their numbers are in 2 different units, you have to use scientific notation here. Okay, you got no other choice. So I'll give you just a moment to go ahead and pencil in those answers really quick. All righty. So another way that we can also use per capita is also by thinking about, let me see. I guess we don't have a slide for that. In your book, they actually have on page 30 population density. And you can look up on Becky's video and she'll go through the answers for population density there. Okay. So the next thing we're going to talk about is proportions. Okay, we're going to expand on that concept of ratios. So proportions are basically saying that two quantities, in other words, two ratios, are equivalent mathematically. So think of two fractions. We know that 1/2 is the same thing as 2/4. The only thing different, it's got a different size denominator. So knowing that, we can use the idea of proportionality to figure out a missing value. So one of the most popular ways that we use proportions and check for proportionality, think about blueprints and maps. Okay, so we have to shrink them. We're scaling something. All right, so if we look at this problem right here, in this case, it says the distance between Lafayette and Vincennes is 160 miles. That's represented by 6 inches on the map. Now, if the distance between Lafayette and Fort Wayne is 4.5 inches on the map, how far are they apart in real life? So what we're going to do is we're going to use one set of information to help us calculate if they are in proportion. If the inches equal a certain mileage, I should be able to calculate the mileage if I know the inches of a different distance, okay, to another location. So to set up a proportion, what I recommend is this first method. So this is the one on the top on page 31. So the first thing you want to think about are what are the two things that I'm comparing? I'm comparing inches and miles. Now it doesn't matter what order you put it in to begin with. In this case, they just so happenly had inches in the numerator and miles in the denominator. You could have had them flipped. It doesn't make a difference as long as the other side of the proportion matches the same order. So notice they're the exact same order. Now what I want to do is fill in what I know. Now I already know both numbers for Lafayette to Vincennes. So on this one side, I'm going to fill in Lafayette to Vincennes inches and miles. Now for the other side, going Lafayette to Fort Wayne, I only know the total inches. I'm trying to figure out the mileage. Since that's the thing I know the least about, that's where I'm going to put my variable. And I mean, it really doesn't matter which letter you use, but we like to use X in math. So that's why we put an X. Okay, so now I've got a proportion, and what I'm going to have to do is solve this proportion. So now we're going to do just a tiny little bit of algebra. I've written out the long version here so that we all can understand what we're doing, and then I'll talk about the shorter version in a moment. So the first thing we want to do is set up our cross multiplication problem here. What I like to do is always start with the diagonal that includes the x, okay? Because we like to see at the very end x equals something. So 6 times x gives me 6x is equal to, well, the other diagonal, when I multiply these, that's 160 times 4.5. Okay, so the first thing I'm going to do is I'm going to multiply those out and get 720. Now I need to get x by itself. So to get x by itself, I need to undo this multiplication by dividing with the number 6. And since this is an equal sign, it's saying that one side is equal to the other. So whatever I do to one side, I have to be fair and equal and do it to the other side too. So I divide both sides by 6. And in this case, the 6's cancel out on the left-hand side. And I wind up with x is equal to 120 miles. Okay. So basically what you're going to be doing every single time that you're going to be calculating an unknown amount using a proportion, the first thing you're going to do is multiply the numbers across from each other, and then you're going to divide with the number across or diagonal from the x. Okay? Always that order. Multiply the numbers diagonal, then divide with the diagonal with the x. Okay? That's basically what we just did here. and that'll help you get that answer. The other version is to put both units on the same side, but then the numerators have to match and the denominators have to match with what you're looking at. So in this case, it was how you were driving, Lafayette to Fort Wayne or Lafayette to Vincennes. To me, this one is a little bit more confusing, and most students gravitate to the first one. So that's why we usually use the first one. As long as I get the two units that I'm comparing, match the other side in the same way, and just start filling in what I know. Okay, so let's look at another example. Okay, here's another one with a map. So on your map, the distance between Evansville and Muncie is 8.75 inches. How many miles is it from Evansville to Muncie? If it's 4.5 inches between Lafayette and Fort Wayne, and 120 miles. So once again, I've got inches and miles. The side I know the most about, in this case, Lafayette to Fort Wayne. So that's 4.5 inches and 120 miles, Lafayette to Fort Wayne. On the other side, I know the inches. I'm trying to figure out how many miles. So I'm going to multiply the two numbers across from one another. I'm going to divide with the one with the x, and I get approximately 233 miles. All right. Here's another one, ordering food for a party. Okay, a couple ordered 70 ounces of pate for their engagement party of 45 people. It was such a hit that they decided to serve it again at their wedding, but at their wedding, they are going to have 315 people. So how many ounces do they need to order? Well, what am I comparing? I'm comparing the ounces of the food and the people, the number of people. So I've got ounces over people, or you could have had it in the opposite order. Okay, as long as the other side matches the same order. So 70 ounces goes with 45 people. So on the other side, I already know 315 people. I'm trying to figure out how many ounces. So multiply the numbers across from each other diagonally and divide with the one with the x. And I get about 490 ounces. Okay. Let me see. This one, oh, I like this one. Okay, a house was assessed at $73,000 and it has an annual property tax of $1,600. How much would the property tax of the owner of a house in the same neighborhood expect to pay if his house was assessed at $87,500? Okay, so what am I looking at? Tax, the property tax, and the evaluation of the home there. Okay, so those are the two things. So keep them in the same order on both sides. We know that 1,600 goes with 73,000. I'm trying to find the tax on an $87,500 home. So cross multiply, then divide with the one with the x. And in this case, I get $1,917.81. Okay, and I'm just going to show one more here up on the screen. Let me see. This one here. Credit hours taking at Ivy Tech. So take a look at that one. I'm just going to double check all my my attendance here. Okay. So definitely know how to set up a proportion and solve a proportion. Now don't forget you've got homework due tomorrow. Make sure you get that done. If you don't get it done in time, it does shut off. So be careful. Don't wait till the last minute. And if there's a quiz out there that you need to do, remember you do get 2 chances to take a quiz each time, but you got to take it before it's due. Okay, so that is all the time I have left with you. I'll stick around if you have any other questions. Otherwise, you're free to go. Have a great 3-day weekend.